speaker is Peter Williams, and the talk is entitled Extreme Activity in Extreme Objects, Radio View of Cool Star Magnetism.
Okay, thanks. Yeah, so I want to talk about looking at magnetism in very cool objects, in fact, not stars anymore, but brown dwarfs, and using ZBI that's not going to come up at all in this talk. So for the initial context, this is a proposition I want to make. When we're talking about the very cool objects, so ultra cool things that are spectral type 7 or later is kind of a catch-all, because some of them are stars, some of them are brown dwarfs, some of them we don't actually know because we don't know their ages. It gets really hard to study. X-ray emission really falls off a cliff. So this upper plot here will get X-ray emission as a function of spectral type. Here, normalized by bolometric luminosity, which is often what you talk about when you're doing comparisons of, talking about stellar X-ray emission as an activity measure, or just in terms of absolute luminosity, not dividing. And once you get to, well, it's kind of interesting. One thing is, if you're not normalizing by bolometric, once you get to around the fully convective boundary and 3.5 or so, every spectral subtype you're going down by about a factor of 10. And if you normalize by bolometric luminosity, the cutoff is a little bit later. So either way, you're really, there's been 4 photons ever detected from an L dwarf, plus or minus 1 as well might be background. But X-ray is really hard. H-alpha gets very faint. So iron hydride spectroscopy, that can work through the L dwarfs. Yeah, so in general, also once we get to this regime, objects are rotating very rapidly, so that can cause problems for various spectroscopic approaches. And if you want to say, okay, sometimes we can monitor something in the optical and infer about its magnetic activity by saying that variations are due to spots. Once you get into this regime, clouds start playing a role. And so the difference between clouds and spots is not always obvious. Radio emission is not perfect, but it's one of the relatively good options that we have for probing magnetic activity observationally in the brown dwarf regime. So this green line is just sort of extrapolating that fall off in the X-ray emission from the previous slide. And here it looks much steeper because we're talking about much later spectral types at this point. And so what we show here is there's certainly a lot of upper limits when you observe brown dwarfs as very cool stars in the radio, but we do have some detections. And sorry, there aren't many units here, but even so, I'll be talking about this object, a T6.5 dwarf, a lot. But obviously, it's variation. There may be some kind of trend, but the luminosities are, at least in some cases, comparable regardless of your effective temperature. And one thing I want to point out is currently there's only one published object this late, but Greg Halman's group is going to be adding, I think, 4 more late L and T dwarfs to the radio detected sample. So it's still not easy peasy, but this is something that we can do in the radio that is really hard to do using any other method. Another interesting thing is that the data are showing auroral phenomena. So this is getting back to Sanders' observation. So this is Saturn observed in the UV, and this is its auroral oval. And you can see there is a full oval, and then there's moving spots depending on activity there. And so one thing that's associated with this kind of auroral activity is bursty coherent radio emission. So this is not actually auroral emission, but okay, so here we have a dynamic spectrum from AD Leo. So we're seeing time is progressing to the right, and then the radio spectrum goes up and down. So as a function of time, what we're basically seeing is there's bursty radio emission that's confined to sort of bandwidths of a few hundred megahertz that jumps, it's very time and frequency, jumps around all over. And this is because it's a coherent process. You have a maser, it's a cascade. It's these little kind of pockets of maser emission fire off left and right. And you see this associated with the aurorae in all the magnetic source and planets. They're generally tend to be long wavelength things. Jupiter can be brighter than the sun at long wavelengths. And finally, for actual auroral emission in LA dwarf, here's an example of LSAR 1835. This is the object that Alexei is looking at. And so here is its radio circular polarization as a function of time. And what makes us associate it with auroral emission is the fact that there's this periodic structure which happens at the rotation period of the object. And one consequence of this emission is circularly polarized. It's also highly beamed. And so every rotation, the beam of radio emission is kind of like a pulsar. The beam of radio emission swings into view, you get a burst. And the other thing about this is it's this coherent process that's intensely bright. That's why Jupiter is brighter than the sun. And that's why we can see it even in these cool late objects. And one of the big questions in talking about these kinds of objects is trying to understand, to get this emission, you need non-thermal energetic electrons and understanding where those come from. An emission like this is coming from reconnection of the corona. Something like here, so what this paper is actually about is there's some structures here that kind of move faster than rotation, and that's taken as evidence that the acceleration is happening in reconnection of magnetotail of Saturn's magnetosphere. So this is the kind of thing where if we could say probe these auroral ovals, you could understand for things that are presumably free-floating and not being bathed in the solar wind, you can understand what's accelerating these particles. We really don't have a good explanation for that yet. Another thing I want to point out is just sort of in a theoretical sense, so these kind of periodic radio bursts that we see, you can interpret them as kind of being associated with magnetic loops. So here's a set of so here's some actual data of another famous kind of radio pulsing M dwarf where we see again a periodic burst, and this is another dynamic spectrum with the radio spectrum vertically and time progressing to the right. And what you can do is you can say, all right, we associate the emission, the maser emission comes from kind of the base of a magnetic loop where you have a field-aligned current. And based on the properties of the spectrum in terms of its phasing, whether there's a frequency drift, the polarization sign, you can infer some properties about the magnetic loop. And so this is, if you assume a loop configuration like this, you can basically reproduce the observed spectrum. And important caveats, that certainly this is not a unique solution by any means. But interestingly, so this paper that looked into this, for a few of these objects, they looked at this and whatever, I forget which. They don't get they can't reproduce the data with a single dipole. The loops have to have different inclinations relative to the rotation axis. Given that it's not a unique solution, and this is not a super detailed model, that's not a sure thing. But they certainly tried to do it to use a single dipole. They could manage it. So, in terms of the coolest object that we have, as I mentioned before, we have a T6.5 dwarf, 2 mass 1047. Its effective temperature is about 900 Kelvin. So the history of this object, it was observed in the radio by my advisor, Ida Berger, a while ago, got sort of an upper limit. Then Matt Root and Max Fulchen observed it with Arecibo and detected 3 radio bursts. So 1 millijansky in is radio for pretty bright over the course of 13 months. And so once again, we have a dynamic spectrum, and you see these kind of bursts evolving on 100-second timescales. Now, unlike previous objects, unlike what I was showing before, these are spread out over the 13 months. They searched for periodicity, but couldn't find it. Arecibo, because it's in the ground, you can't point it. So you can only observe one object for about 3 hours. So it's hard to measure rotation period of anything with Arecibo. But because this is by far the coolest object that has been detected in the radio, we're certainly interested in seeing whether there is periodicity, trying to understand whether the properties of the magnetic field that we infer from the radio data, whether those are consistent in a 900 Kelvin object as they are, let's say, a late M dwarf. That's a question. And the answer is basically yes. So we have some new VLA data. So these are light curves in the radio. So the top panel is showing, so the red is Stokes total intensity, and blue is the Stokes circular polarization intensity. And the fact that these peaks are approximately about the same shows us that we're getting essentially 100% left circular polarized emission. So here I've broken it down by, we observe in two large bands centered at 5 and 7 gigahertz. So you can see these peaks have somewhat different frequency structure. And the overall view is we've just done a simple phase dispersion minimization pull-out period. So these lines kind of mark periods at that. So the best fit is 1.77 with about 2% uncertainty. Although obviously the peak structure varies. And one thing I'll point out is, say this doesn't look like much, but that is statistically significant. You have several observations in a row, and you look here, where sort of in the interpeak regimes, the mean is really 0, and this does actually this is not much of anything. So we do seem to have some periodic structure. Now, if you look at the exact peaks of these things, again, clearly not lining up precisely with that phasing, and the structure is changing. So that 2% uncertainty is kind of a by-eye assessment. If you do something formally, you get something much smaller, but that doesn't really capture the fact that there's all this variability here. So zooming in on these things, so I should say this previous plot has a lot of averaging. Zooming in here, we see the detailed structure. Again, this is a different way of showing the frequency structure. And so something like this, you can imagine there could be a frequency drift in the pulse. And so earlier, it's at higher frequencies, and later it's at lower frequencies. And so again, so we're zooming in on time windows. So this is the phasing proceeding in time. And so for instance, this peak here, again, this doesn't look like much, but it is statistically significant. And this corresponds to this part here, which is sort of ahead of the nominal. These data up here are things at higher frequencies. Again, this is especially kind of minor, but you do see pulses at that same periodicity. And so the magnetic field that you infer from these pulses is basically the second frequency. 10 gigahertz is giving you a magnetic field strength of 3.6 kilogauss. So we've got something that's about, I think it's 6 times the effective temperature of Jupiter, and its magnetic field is 500 times stronger. So again, this one, so we see that there's not much of anything here. But in general, the interpretation that I want to give to this is, again, this maser process, it's this coherent cascade. It's very variable, depends a lot on tons of little maser emission sites. So I want to interpret this variability as showing just that in any individual rotation where the radio beam is aligned with us, it can look very different. And so that does mean that if you're trying to measure a rotation period really precisely in this method, you have to be careful. But the basic takeaway is these 5 are significant, and that certainly is good enough for me to call periodic. One thing I want to add, though, is if you want to get adventurous with your interpretation, here's averaging the 2 frequencies. So if we assume a somewhat shorter rotation period, you can line up the peaks better for these first 3 than your worst for these. If you add a little phase jump, you can recover a better fit here. So you can imagine in that loop model, maybe there's some kind of burst of particle acceleration at a time before here that happens to light up radio emission from one magnetic loop. And then maybe this decrease in amplitude is a fading of that burst of particles. And then maybe there's another burst. Maybe you see the same thing, it's lighting up a different loop at a different longitude. But you have to kind of assume that these things are nice and non-overlapping. So I don't think there's any good reason to prefer that interpretation to just things at a single periodicity with just a variable pulse structure. So if we take that rotation period, and here we've converted it to a V sin I, and so here's radio spectral luminosity versus V sin I. Again, so this is this is the most rapidly rotating radio detected brown dwarf compared to things that again have been detected. No obvious trend there. This is just a 6th rotation period measured for mid or late T-dwarf. And the rest have been done with in the infrared. And their cloud variability sort of makes those rotation period measurements a fair bit more uncertain. And there's no apparent relation between the rotation period and luminosity, clearly, which is interesting that there's some data from the X-rays that you may be sort of reaching a supersaturation region in the rotation activity relationship when you look at the coolest objects that you can detect in the X-rays, but we don't see that in the radio. Now for something completely different, I just want to briefly advertise another product that I have, which it's too complicated to fit into a 20-minute talk at all, so I just wanted to mention that I've also, in the past year, been working on a detailed study of this binary NLTT 33370. It's young, it's a visual binary with an orbit of around 3 or of a few years. We don't know it yet, but we'll be able to measure the component masses. It's hyperactive, so here's an SED spanning more than 9 orders of magnitude in wavelength. We have X-ray observed, so it's the brightest ultra-cool dwarf in the radio. It's also extremely X-ray bright. And this paper has all sorts of crazy detailed observations. So you should just check out the plots if nothing else. In general, this ties in with talking about the auroral interpretation of things, where these kind of detailed simultaneous observations of different bands can really help us understand what's going around in the planetary magnetosphere, ionosphere, and understanding what's driving the radiation, what's accelerating those particles out there. And that can help us understand, our understanding of the field topology can help understand what's going around in the planetary exosphere, and vice versa. Our understanding of phenomenology can help us understand the topology. So I'll put up a summary, and thank you for your attention.
First question.
Can I take you back to your totally different system?
Sure.
What's the evidence of injection of plasma, cool-dense torus, at the bottom?
So we observed the radio emission over the span of 2 years, 2 long observations separated by a year. Both times we also had simultaneous optical observations. And you see optical oscillation, and you see kind of an underlying, basically it's sinusoidal optical, and you see an underlying radio modulation with a bunch of flares too. The second year, though, the circular polarized emission stays in phase with the optical, but the total intensity has sort of a notch. Like there basically seems to be the best. It's very complicated, so you can spin a lot of interpretations for sure. But the best interpretation that I could come up with is that there's a certain decrease in the emission, in the radio emission at a certain phase that's kind of consistent with some kind of persistent, that's consistent with a kind of persistent radio structure. And so the best way I can think of to get that is if you have an equatorial torus that's absorbing the radio emission, because as it rotates, sometimes the torus subtends a larger fraction of the disk.
Looks surprisingly like a prominence. I'm sorry, I just had to say that word. You would see the same thing with that prominence. You'd also see occultation of the X-ray emission as well.
Yeah, I don't think we have the X-ray data to test that. So I think, I believe Jupiter and Saturn have kind of dual equatorial tori. So it's sort of what's driving that idea.
Okay, another question.
I was actually wondering how well resolved you have this particular variable radio emission in terms of how wide is it in frequency space, and does it maintain the same width all the time, or does it get wider, or does it seem to shift at all?
For the T-dwarf, the sensitivity is such that we don't have a very good handle on that. We have we've got sort of the emission in the 5 and 7 gigahertz, so you can see that it's about constant around those levels. Yeah, this is a fairly faint object, so we don't have a whole lot.
I'm not familiar with the loop model, but from the planets, what I expect is that you have solar connection occurring at the magnetotail, and then you have the electrons that are released, and they precipitate and generate a moment. The loop models, if I understood correctly, the magnetic lines are closed. Where are the electrons coming from?
Yeah, so the model is certainly not worked out in, so I mean, it doesn't have to be a full loop. So one reason that they do prefer that is sometimes you see radio pulses where one is left circular and one is right circular polarized. And the idea there is that you're seeing two different foot points of the loop. And so you get different circular, but we don't see that here, so it doesn't necessarily apply here. And if you're only seeing one pulse of one polarization, it could be an open field line, electrons streaming along. Or you can imagine some kind of Jupiter Io situation, or you can spend all, you can talk to Christian Helling's group and come up with a million different ways to get some energetic electrons in there. The fact that the field lines are closed in that model, it is relevant in some of the data, but it doesn't have to be the case.
Any other questions? I think we'll thank Peter and Irina, welcome. And the talk will be cyclotron.